Welcome to the sixth lecture of General Chemistry. Today we're going to be talking about aqueous chemistry and different types of chemical reactions, such as precipitation reactions and redox reactions. Now, if the title is throwing you off a little bit, don't worry. There'll be a short video in a few slides that'll hopefully explain it to you. Let's start with some review questions from the material we covered last time. Which of the following homonuclear diatomic molecules will have a shorter bond length for the -1 anion than for the neutral molecule? Okay, to answer this question, we need to use molecular orbital theory. And there are two patterns when you use molecular orbital theory. So we have this pattern, sigma, sigma star, pi, sigma. And remember, these are for 2s. This is for 2p. You have pi star 2p and sigma star 2p. And then there's also this pattern, which everything oxygen, O2, and right on the periodic table in the second row, we use this pattern. I'm not going to label those again. They're the same labels as on the diagram on the left. So let's look at lithium-2. Lithium-2 has 2 electrons, one from each lithium atom. Molecular orbital diagram would be this. The bond order would be 1 for lithium-2. Now, when we look at lithium-2 minus, we add 1 electron. That electron will be added into a anti-bonding orbital, so the bond order will decrease, and that would be 0.5. So the question's asking for a shorter bond, which means it would be a stronger bond and a higher bond order. So choice A is not correct. Let's look at choice B, C2. Carbon each has 4 electrons, 4 valence electrons. So C2 molecule will have 8 that we need to fill. 1, 2, 3, 4, 5, 6, 7, 8. So C2, the bond order is going to be 2. Bond order would be 2. For C2 minus, we add 1 electron. You see that it's added into a bonding orbital, so our bond order is going to increase, and that would be 2.5 now. So the C2 minus anion will have a shorter bond length than the neutral molecule. And we can try, just to be complete, let's go through N2. N2 will have 10 electrons. N2 minus, we add 1 electron, and you see that it's in an anti-bonding orbital, so that's actually going to increase the bond length, not shorten it. And oxygen, O2, we fill 12 electrons, but now we use this pattern. So we have 1, 2, 3, 4, 5, 6, 7, 8. Sorry. Missed an orbital there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. And this is the pi star anti-bonding orbital. So when we look at O2 anion, we add another electron, and that's added into the anti-bonding orbital, and that would destabilize the bond, make it weaker, and make it longer. So the correct choice is C. Okay. Here's the final review question for today. What is the hybridization of each atom, each carbon atom in glycine? So take a few moments and answer this question. All right, when we look, let's look at this carbon first. What's the steric number on the carbon? Well, it has 3, it's bonded to 3 other atoms, and there's no lone pairs, so the steric number is going to be 3. We need 3 equivalent hybrid orbitals. That would be an sp2 hybridization. Now for carbon, the second carbon, it's AX4, steric number is 4, so it's going to be sp3 hybridized. We have 1 from the s, 3 from the p's, 4 total hybrid orbitals. Now let's just, to be complete, let's look at the oxygens in the nitrogen. And I'll add in the unpaired electrons here, because those are important. So the nitrogen, what is its steric number? Well, it's bonded to 3 other atoms, so that would be an AX3, but it also has 1 lone pair. So its steric number is going to be 4, thus it has to be sp3 hybridized. This oxygen, it's only bound to 1 carbon, so AX, but it has 2 lone pairs. So its steric number is 3, and it has to be sp2 hybridized. And finally, this oxygen, bound to 2 other atoms, but it has 2 lone pairs, so its steric number is 4, sp3 hybridized. All right, just to bring this slide up again to remind us what point of the class we're in, we talked about chapter 11 last time, and this really marks the point where there's a definite shift in what we're going to be talking about in the second part of this material towards the second exam. So all the material up to now is sort of built off each other from chapter 7 on. Now we're going to go back and cover material from chapter 4. And just to remind you, the review that we really didn't cover in class from chapter 2, chapter 3, this is when that material is going to become important. So today we're going to be covering these sections in chapter 4, 4.1 to 4.3, and then 4.5 and 4.6. Now we're not going to talk about 4.4, that's acid-base chemistry. We'll be talking about that next time, and we're not covering section 4.7 in this class at all. Let's start off with 4.1, talking about water. Earth is covered by approximately 75% of its surface is covered by water. And if you want to see a very large number in nature, the amount of water on Earth is about 1.5 times 10 to the 21st liters. It's an enormous amount of water. And cells in our body are about 70% water. And that's no coincidence that the cells in our body and the Earth's surface are roughly the same percentage of water. Life arose on the surface of the Earth, so it really used all the elements that were available to it. So what are some properties of water? Well, at Earth temperatures, generally it's liquid. Water has a high heat capacity. That means it holds onto heat very well, transfers heat very well. It has the ability to dissolve molecules. It expands when it freezes. So all of these properties are responsible for life being able to survive on Earth. And they're also responsible for many of the geological features we see on the planet. All natural waters, fresh or salt water, have ionic and molecular compounds dissolved in them. So now we're going to see a short video which hopefully will explain to you the choice of title that I chose.
Have you ever seen a commie drink a glass of water?
Well, I can't say I have.
Vodka. That's what they drink, isn't it? Never water.
Well, I believe that's what they drink, Jack, yes.
On no account will a commie ever drink water, and not without good reason.
Yes. I don't quite see what you're getting at, Jack.
Water. That's what I'm getting at. Water. Mandrake, water is the source of all life. 7/10 of this Earth's surface is water. Why, do you realize that 70% of you is water? And as human beings, you and I need fresh, pure water to replenish our precious bodily fluids. Are you beginning to understand? Mandrake. Mandrake, have you never wondered why I drink only distilled water or rainwater and only pure grain alcohol?
Well, it did occur to me, Jack, yes.
Have you ever heard of a thing called fluoridation? Fluoridation of water?
Yes, I have heard of that, Jack, yes.
Well, you know what it is. Do you realize that fluoridation is the most monstrously conceived and dangerous communist plot we have ever had to face?
If you've never seen that movie, it's that clip is from Dr. Strangelove, a Cold War era movie. And just a little background, General Ripper is obviously insane, but he thinks there's a communist conspiracy to contaminate drinking water by fluoridation. So he sends the bombers to attack Russia preemptively, a nuclear strike. And Colonel Mandrake here is trying to stop him. But in honor of Jack Ripper, General Jack Ripper, today we're going to devote some of our practice questions on precious bodily fluids. Let's talk about solutions. What are solutions? They're homogeneous mixtures of two or more substances. The important definitions when we talk about solutions are solvent, and that's the substance that's present in the greatest quantity. And the next term that's important is solute, and those are the substances that are dissolved in the solvent, or that are, if you're talking about two liquids, they're the substances that are there in the lesser quantities. And today we're primarily going to be talking about aqueous solutions, and those are solutions where water is the solvent. If we look at a picture from your book that that tries to explain a solution, we see that when you take sugar, which is a solid, and you add it to water, the sugar dissolves. And this gives a homogeneous solution. That is, the solution, you take a solid and a liquid, you mix them, and what you get out, the whole thing is liquid. It's all one in one physical state. In this example, water is the solvent and sugar is the solute. Water is a polar molecule. And if you remember, we talked about polar bonds. So water has polar bonds, but it's also in a geometry where it has a net dipole. So it has uneven electron distribution, as we talked about, polar bonds, and it's in a bent molecular shape. So it has that leads to a net dipole. Water readily dissolves a variety of substances, and we'll see some examples of those in a second. And it strongly interacts with its solutes, and it often plays a very active role in aqueous reactions. So if we look at some electron distributions of certain molecules, here's the electron distribution of H2. It's symmetrical, as you'd expect. Both atoms in this molecule have the same electronegativity, so you get equal sharing of electrons. But when we look at water, we see that charge distribution is asymmetrical. There's a partial negative charge near the oxygen and partial positive charges near hydrogen. That leads to dipoles, bond dipoles, and because of the bent geometry, water has a net dipole shown here. Figure 4.2 shows what it's like on a molecular level when an ionic compound dissolves in water. And the negative ion, shown here, water interacts with that negative charge by putting the positive dipole side of the molecule towards that negatively charged ion. So it forms a cage around it, in a sense. Water can also interact with the positive charged ion in the ionic compound when it's dissolving, and this time it faces that positive charge with the negative dipole side of the water molecule. So in this way, water actively dissolves the ionic compound. It can pull away these negatively charged ions and positively charged ions from the ionic compound. And this is what the process of an ionic compound dissolving is caused by, is this ability of water to pull these charges out. And normally a charge wouldn't want to be by itself in nature. There should always be a counter charge to it. In the water, the polar water molecule acts to counteract the charge. And here's an example of how water can do the same sort of thing with an uncharged molecule. Now we have NH3. So NH3 does not have, it doesn't have charges, but it is a polar molecule. It has polar bonds, and it has a geometry which gives it a net dipole. So you see that the water molecule aligns itself. The negative side of the water molecule aligns itself with the positive side of the ammonia atom. And the positive dipole side of water molecule aligns with the negative dipole side of NH3. And this ability of water to interact, it's really how life is possible, these polar molecules. An example of this would be how the lipids in your body that have a polar group and a nonpolar group, they interact with one another by basically having the polar group that can interact with water on the outside and this nonpolar group on the inside. So when you get a bunch of lipids together, they'll form what's known as a micelle or a liposome, where the nonpolar groups face each other and they make a bilayer. They're trying to drive away water from these nonpolar regions, and the polar regions are sticking out in solution. In this case, it forms the outside of your cell. And this is really what allows your body to have the necessary equipment inside a cell and keep it there and be able to control that environment. Let's talk about concentration units. So a concentration defines the amount of solute in a solution. So you can talk about amount of solute in amount of solvent, or amount of solute in amount of solution. And most commonly, we're going to be talking about the solute per total solution. And most commonly, you base these concentration units on mass or moles. A concentration unit that's based on mass would be ppm. ppm is grams of solute per million grams of solution. So we're really talking about the mass of the solute divided by the mass of solution. These are very useful for small amounts. And an analogous term would be parts per billion. Now this is a gram of solute per 10 to the 9th gram of solution. And these values you'll see a lot if you're in environmental chemistry, sometimes even in medicine, lab testing. But in this class, we probably aren't going to use these units really at all. The unit we're going to be concerned with is molarity, and that's moles of solute divided by the volume of solution. And we can write the number of moles here as a lowercase n. And how do you calculate the number of moles? Well, you take the mass of what you're trying to find, your solute, and you divide that by the molecular weight, grams per mole. So then our equation for molarity then becomes your grams of solute divided by its molecular mass, molecular weight, and that quantity divided by the liters of solution you have. And for small concentrations, sometimes you see the suffix milli, so millimolar, and that's, if you remember, is 10 to the negative 3 molar. And also we've used micro, and that's 10 to the minus 6 molar. So if you see micromolar, that would be 10 to the negative 6 molar, or millimolar is 10 to the negative 3 molar. Let's try our first practice question. In honor of General Ripper, we're going to talk about some bodily fluids. So 500 milliliters of human urine contains approximately 4.6 grams of urea. What is the molarity of urea in human urine? Right, the structure of urea is shown. So the first thing we really need is the molecular weight of urea. and that is 60 grams per mole. So how would we calculate this molecular weight? Well, we simply add up the atomic weights of all the atoms in this molecule. So we have 2 nitrogen atoms, which are about 14 grams per mole each. We have 4 hydrogen atoms. They're about 1 gram per mole each. 1 carbon. Carbon is 12 grams per mole. And 1 oxygen, which is approximately 16 grams per mole. And that's how we get a total of 60 grams per mole. Now the first step, when we're trying to find a molarity, would be finding the number of moles of our solute. And our solute in this case is urea. So the number of moles of urea would be its mass that we have, 4.65 grams. And we divide that by its molecular weight, 60 grams per mole. That gives us 0.0775 moles of urea. Now what is our volume? Our volume's given to us as 500 milliliters. But remember, when we're calculating molarity, it's in terms of moles per liter. So we have to convert milliliters to liters. So we have 500 milliliters. 1 liter has 1,000 milliliters. Milliliters cancel, and we're left with 0.5 liters. Now to find molarity, that's simply the moles divided by the liters, so 0.0775 moles divided by 0.5 liters. And that gives us 0.155 moles per liter. Or you can also write that in terms of 0.155 molar. Molarity can be used as a conversion factor as well. So to find the amount of solute, the moles or the grams that you have in a given volume of solution, you can use the equation from molarity and rearrange it to solve for the number of moles. So we'd have that equation given here, where N is the number of moles, big capital M is the molarity, and volume would be in liters. Now once you know the number of moles, you can use the molecular weight to convert back into mass. Let's try a practice question using molarity as a conversion factor. So the average human body contains 5.1 liters of blood. And this blood has an iron 2 concentration of 2.1 times 10 to the minus 5 molar. What is the mass of iron 2 plus in the average human body? So we know our equation for molarity. So molarity equals number of moles divided by volume in liters. We rearrange this to find number of moles. Remember, capital M stands for molarity, which is a concentration. So we have a concentration times a volume to get the amount of the solute. We're given the volume in liters, and we're given the concentration in moles per liter, so we simply multiply the two. Oops. Yep. Remember, capital M stands for moles per liter. Liters are going to cancel, so we're going to be left with N in terms of moles, which is 1.071 times 10 to the minus fourth moles. The question is asking for the mass of iron, not the moles. So now we're going to have to convert moles into mass, or moles to grams. So moles to grams. How do we do that? Well, we're given the moles. We times the moles by the molecular weight, and that will give us a mass. So the molecular weight of iron is 55.8 grams per mole. And you can find this from the periodic table because iron is an atom in this case. So we take the number of moles we have, multiply that by the molecular weight of iron, 55.8 grams per mole. Moles cancel, and we're going to be left with an answer that's in grams, which would be 0.006 grams of iron 2. And if you wanted to express this in milligrams, that would be 6 milligrams. All right, not a very large amount. But remember, there's also iron 3 plus, and most of the iron in your body is actually in that oxidation state. All right, let's try another question using the same basic concept. How many grams of copper sulfate must you weigh out in order to prepare 100 milliliters of a 0.1 molar copper sulfate solution? And we're given the molecular weight of our copper sulfate complex here. But remember, you could calculate this by just adding the atomic weights of all the constituents. All right, first, let's write our equation for molarity. Now let's rearrange it. We need to solve for moles. And the volume, let's convert our volume into liters. So we have 100 milliliters, and there's 1,000 milliliters in 1 liter. So we get it, so the milliliters cancel, and we're left with 0.1 liters. So now the number of moles we need would be 0.1 moles per liter times 0.1 liters. Liters cancel. We get 0.01 moles. That's the amount of copper sulfate complex that we need. How many grams do we need? Now we convert moles into grams. We multiply by the molecular weight, so 0.01 moles times 250 grams per mole. Moles cancel. We get 2.5 grams, and that would be answer C. Now, it's probably best if you actually write out your conversions, but eventually you'll probably be able to convert really just in your head and know that 100 milliliters is 0.1 liters. Going from milli or killa should become pretty easy for you. But remember, if you're uncomfortable with that, just write out your conversion factors like this and do the dimensional analysis. If we have a solution and we want to make that solution less concentrated, the way to do that would be dilution. And this is a good figure I found that really explains dilution. Solution A here would be our concentrated stock. And you see that there are 20 particles, there are 20 blue circles. And there's the volume, just arbitrarily stated on this figure, says it's 2 milliliters. So what is your concentration? It's 10 particles per milliliter. Now, if we took 1 milliliter of that solution and added 1 milliliter of a solution that just has 0 blue balls in it, we would get same volume, 10 milliliters, but we'd only have 10 particles now. So this concentration would be 5 particles per mil, and thus we would have a 2x dilution. We're diluting it by 1/2. And you can do the same thing if you look at test tube C. If you took 1 milliliter again of our concentrated solution and added 9 milliliters of solution that doesn't have any particles, our concentration would then be 1 particle per mil, and it's a 1 to 10 dilution. And particles, they can be physical particles, they could be molecules, grams, or moles. So you can really you can think of those blue circles as grams or as moles. It works the same. When we look at dilution in a lab, our stock solution, the definition of a stock solution generally is a concentrated solution. That means there's a high solute to solvent ratio. And we use that stock solution to make dilutions. So you prepare a dilute solution by adding solvent to a given volume of the stock solution. And the number of moles of solute remains constant. So if you have, if you're taking out, let's say, a milliliter of your stock solution and there's 1 mole of your solute in that stock solution, the number of moles after you dilute it remains the same. What is changing is the volume. And that's really illustrated here in this equation. This is a very, I'll put a star there because it's a very, very important equation. So M in this equation stands for molarity. But I like writing this equation in terms of C, in terms of concentration. So you have concentration of your stock times the volume of your stock has to equal the concentration of your dilute solution times the volume of your dilute solution. And if you go through the units, each side you have moles per liter times liters. So basically you have moles equals moles on both sides in this equation. So let's look at a physical picture of a dilution. You obtain a certain volume of a stock. You transfer this to a volumetric glassware. You dilute by adding your solvent. And you see that your concentration per given volume is going down. But the number of moles total in that flask doesn't change. All right, let's try a practice question with dilutions. And this is another precious bodily fluids question. The mean normal blood glucose level in the human body is 5.5 millimolar. What happens to the number of moles of glucose when 5.5 millimolar solution is diluted to a final concentration of 0.1 millimolar? Now, this is a conceptual question. Hopefully, you remember from just a couple slides ago, the number of moles doesn't change. Whatever volume you have that you're diluting, that's what's changing. But if you start with, let's say, 5 total moles and you dilute that, you still have 5 total moles. It's just the volume that is increasing to give you a lower concentration. Okay, let's try a question now where we're actually doing some math. Hydrochloric acid is usually a 12 molar stock solution. What volume of that stock solution would be required to make 500 milliliters of a 0.145 molar dilute solution? For this type of question, we're going to use the equation your book gives you, M1V1 equals M2V2. I'm going to write out in terms of concentration. So I'm going to write C1V1 equals C2V2. And why that's useful? It's useful because you can use this equation even if the concentration isn't in molarity. You just have to have the same units on both sides of the equal sign. So we're given C1. Our concentration of our stock is 12 molar. We're given C2. We want to get a concentration of 0.145 molar. And we're given V2, the final volume that we want is 500 milliliters. And what we're trying to find is the volume of the stock that we need. So V1 is what we're trying to find. So we write out our trusty C1 V1 equals C2 V2 equation. Now let's rearrange this before we add any numbers in. Rearrange this to solve for V1. So that will become V1 equals C2 V2 divided by C1. Now you might think that you're given the volume in milliliters, you should convert to liters. But if let's look at the dimensional analysis of this. So you have 0.145 molar, which is moles per liter, times 500 milliliters divided by 12 moles per liter. So the moles per liter cancel, and what we're left with is an answer in milliliters. So you can convert to liters if you want, but it's not necessary. If you don't convert, you just have to remember that the units, your volume units, are going to be the same as the volume units that you're using in the equation. So it's always important to keep your units when you're doing an equation like this. So we should get 6.04 milliliters, and that's the volume of the stock that we have to add, and then we would add 500 minus 6.04 milliliters of our solute. Moving on to section 4.2, writing equations for aqueous ionic reactions. The term electrolyte, this means a substance that dissolves in water and dissociates into ions. And those ions can then carry a charge. That's shown here. In a solution of sodium chloride, it dissolves in water, it dissociates, and these ions can carry an electrical current. So that's shown here by the light bulb lighting up. So strong electrolytes are, for the most part, 100% dissociated into ions. And an example of that is sodium chloride. Other examples are HNO3 and HCl. So in sodium chloride, it's going to be 100% sodium and chloride ions in water. There's also weak electrolytes, and they only partially dissociate ions into ions in water. Now, strong electrolytes conduct electricity very strongly. Weak electrolytes, they're only slightly conductive, and that's shown here. The light bulb sort of lighting up, but not as strongly as before. A classic example of a weak electrolyte would be vinegar, which is chemical is acetic acid that's in vinegar. And you see that it dissociates, it loses a hydrogen ion, but it's not a full, it's not fully dissociated. So we write something that's not fully going to product side of a chemical reaction with this double-headed arrow, and that means there's an equilibrium. And then the other type of molecule you can have is a non-electrolyte, and this is a substance where no ionization occurs and there's no conduction of electrical current. So the light bulb does not turn on. Example of some of these would be sugar, ethanol, ethylene glycol, which is in antifreeze. All right. Question 6, another precious bodily fluids question. There's approximately 3 nanograms of nitrate ion in 1 milliliter of CSF, which stands for cerebrospinal fluid. How many moles of barium nitrate would you need to add to 1 milliliter of water if you were trying to make a solution with the same nitrate concentration as human CSF? The molecular mass for NO3 nitrate is 62 grams per mole, and the formula of barium nitrate is barium NO3, but there are 2 nitrate ions per mole of barium. Our first step, pretty much always your first step if you're given a mass of something, you need to convert it into the number of moles. So we're given 3 nanograms of nitrate. So we need to convert that into grams. So 3 nanograms, 1 gram has 10 to the 9th nanograms in it. Or you could also do, if you want to remember it the other way, 10 to the minus 9th grams is 1 nanogram. So we have 3 times 10 to the minus 9th grams of nitrate. We divide that by the molecular weight. So the molecular weight is 62 grams per mole. And how do you know that you need to divide by the molecular weight? Well, you look at the units. Grams are going to cancel. Dividing by 1 over mole, the mole flips up, so that would be moles, would be your final unit. And you would get 4.8 times 10 to the minus 11th moles. And that's of NO3 minus. That's in 1 milliliter of CSF. And now we're asked, how many moles of barium nitrate would you need to add to the same volume if you're trying to make an analogous solution. So we don't need to consider volume because we're looking at the same volume in both cases. We have 1 mil of CSF, and we're trying to make a 1 mil solution of barium nitrate. To answer this question, we know we have 4.8 times 10 to the negative 11 moles of nitrate. That's what we need. But now we need to look at the molar ratio of nitrate in the molecule barium nitrate. So 4.8 times 10 to the minus 11th moles nitrate. And the molar ratio would be 1 mole of barium nitrate contains 2 moles of actual nitrate ion. That you can tell that by the 2, the subscript 2. So that becomes 2.4 times 10 to the minus 11th moles of barium nitrate. So we're going to have to add half as many moles of barium nitrate to get the same nitrate ion concentration that's in the CSF. All right. Next question. What is the molarity of nitrate ion in a 0.0525 molar solution of silver nitrate and of aluminum nitrate? So the first thing to determine is the chemical formula for silver nitrate and aluminum nitrate. So silver nitrate is going to be AgNO3. That's because the silver has a +1 charge, and the NO3, the nitrate ion, has a -1 charge. Aluminum nitrate, now it's going to be AlNO3 3. It's because aluminum has a +3 charge. Looking at where it is in the periodic table, it's going to lose 3 electrons to get to a noble gas configuration. And nitrate ion, remember, it has NO3 has a -1 charge to it, so you need 3 of those to equal the charge of aluminum. So let's look at the molarity of nitrate ion in each of these solutions. So the first, we have 0.0525 moles of AgNO3 per liter. Now then we need to use the mole ratio in the chemical formula, and that would be 1 mole NO3 per 1 mole of AgNO3. So we're just multiplying by 1. So this becomes 0.525 moles per liter of nitrate ion. Now aluminum, we do the same process. 0.0525 moles of AlNO3 per liter. We multiply by the mole ratio, but now we have 3 moles of NO3 in every mole of AlNO3 3. How do we know that? That's because of this 3 here. That's telling us there are 3 moles of NO3 in every mole of this compound. So we multiply 0.0525 by 3, we get 0.1575 moles per liter of nitrate ion. And remember, these are strong electrolytes, so they completely dissociate in water, leaving their free ions. We can write equations, chemical equations, for these aqueous ionic reactions. The molecular equation, this shows all reactants and all products as if they were intact, undissociated compounds. And this particular type of equation gives the least information about the species in solution. If we look at the reaction of silver nitrate and sodium chromate to form silver chromate and sodium nitrate, this would be the molecular equation. We're showing the compounds as if they were still intact. But this isn't true. These are strong electrolytes. They're dissociated in water. And I should mention here, this AQ stands for aqueous. This means that the silver nitrate and the sodium chromate are in aqueous solution, meaning they're dissolved in water. Here we see an S. That means solid. So these are physical states of our compounds. And again, the sodium nitrate is aqueous. It's dissolved in water. So what does this look like? When you have solutions of silver nitrate and sodium chromate, they mix. You notice that a solid forms, and that solid is silver chromate. So we can write what is called a total ionic equation if we want to gain some more insight into what species are dissociated. And this gives the most accurate information about species in solution. So if we take the same example we had on the previous slide and write that as a total ionic equation, this time we have to write all the ions as they're dissociated. So silver plus, NO3 minus, sodium plus, CrO4 2 minus. And notice that we are still including the physical state of those ions. They're aqueous, meaning they're dissolved in water. And you notice now that the solid, we keep that compound together. It's not dissociated, so we write it out as its full compound. An important term for the total ionic equation are spectator ions. And these are ions that are not involved in the chemical change. That's why they're called spectators. And they appear the same on both sides. So the same physical state and the same charge. And let's see, what are the spectator ions in the above example? Well, we see that sodium plus is aqueous on both sides, and NO3 nitrate ion is the same on both sides of the equation, so they can cancel. So when these spectator ions cancel out and you remove them from the total ionic equation, that becomes what is known as the net ionic equation. So for the reaction that we've been looking at, the net ionic equation would become silver plus CrO4 2 minus becomes silver chromate. And this is really just showing the chemical change that is occurring. You have aqueous silver ions, aqueous chromate ions, and they're turning into a solid silver chromate. Figure 4.4 in your book illustrates aqueous ionic reactions in the three types of equations. So you have the molecular equation, silver nitrate, sodium chromate, going to silver chromate solid, and sodium nitrate aqueous. So here we see that the forming the solid silver chromate, they're written in purple, the rest is in black.
If we want to show the total ionic equation again, you show these as they're fully dissociated. And the net ionic equation is when you subtract your spectator ions from your total ionic equation, and this is really just showing you what chemistry is occurring. Moving on to section 4.3, precipitation reactions. And we just saw an example of a precipitation reaction. So what is a precipitate? It's a solid product that is formed from reactants in solution. Example, we just saw one, but another example would be if you had silver nitrate and silver chloride, both aqueous, dissolved in water. When you mix these two solutions, you would get sodium chloride solid and be left with sodium nitrate dissolved aqueous. Can you predict the formation of a precipitate? And you can. You have to use the solubility rules. So what are some of the guidelines to follow for solubility? Soluble cations. Group 1, so the first column in the periodic table, known as alkali metals, they're soluble, and as well as NH4+, ammonium, the ammonium ions soluble. What about anions? NO3, nitrate, and C3COO-, which is acetate. Those are soluble anions. The halides in group 17, or 7A, they're going to be soluble for the most part, except when they're present with the following cations: silver plus, copper plus, lead 2+, and mercury 2+. So that's a rule. It's really just something that you have to remember, that the halides are going to be soluble except with silver, copper, lead, and mercury. Same goes for sulfate, SO4 2- ion. It's going to be soluble except lead, mercury, calcium, barium, and strontium. And calcium, barium, and strontium are all group 2 metals. So combining anions and cations not listed above will result in the formation of an insoluble compound. So what are some insoluble compounds? Some examples. Well, all hydroxides, that is OH-, things that are combined with OH-, are going to be insoluble except for the group 1A, and group 2A, calcium, strontium, and barium hydroxides. So group 1A and group 2A, calcium, strontium, barium, those will be soluble. All other hydroxides will be insoluble. All sulfides, that is S2-, those will be insoluble except, again, group 1A and ammonium and calcium, strontium, and barium. Those are, again, group 2A. And you should see a pattern there. All carbonates are insoluble except 1A, when they're combined with 1A metals or ammonium. And all phosphates are
insoluble except, again, when they're combined with 1A metals and ammonium. So let's look at precipitation. When you combine a combination of non-soluble cation with a non-soluble anion, you get a precipitate. And in this example, we have sodium iodine, sodium iodate, and lead nitrate in solution. When we combine the two solutions, what you see is a yellow precipitate forming, and that is lead and iodine anions coming together and forming the lead iodine precipitate. So what cations do we have? We have lead 2+, sodium+, anions nitrate, NO3-, and iodate, I-. Nitrates and group 1A metals like sodium are always going to be soluble. What isn't soluble would be lead 2+, and the halogen I-. So that's where the precipitate lead I2 comes from. So let's look at a net ionic equation for this reaction. So soluble ionic compounds would be strong electrolytes. They ionize completely in aqueous solution. And you can write total and net ionic equations. So if we write the molecular equation for our previous example of lead nitrate and sodium iodate mixing, the total ionic equation would be lead 2+ plus NO3-, the nitrate ion, plus sodium plus I-. So this side we're writing as they're totally dissociated in water. The product side becomes now lead iodine solid, and sodium and nitrate are still aqueous. We can take out our spectator ions, the nitrate and the sodium, and then our net ionic equation becomes this. Lead 2+ plus 2I- goes to lead I2. Let's try a practice question. Does a precipitate form when sodium chloride is mixed with silver nitrate? If so, write the net ionic equation for the formation of the precipitate. So if you remember your solubility guidelines, group 1A ions, alkali metals, they're always soluble. A nitrate anion is going to always be soluble. Halides are usually soluble except when they're combined with certain cations, and one of those cations is silver. So in our case, silver and chloride, when they're mixed, they're going to form a solid precipitate. So first, let's start with the molecular equation. So molecular equation would be NaCl aqueous plus AgNO3 aqueous, and this will go to NaNO3 aqueous plus our solid AgCl. Next step would be writing the total ionic. And in this, we just break apart the complexes that are in the molecular equation. Na plus aqueous plus Cl minus aqueous plus Ag plus aqueous plus NO3 minus aqueous goes to Na plus
aqueous plus NO3 minus aqueous plus AgCl solid. And that's important to remember that you have to include those, the physical state, the aqueous or solid of every ion. Now we look for the spectator ions. Sodium is on both sides, and nitrate, both sides. So we can then take those away and write our net ionic equation, which would be Cl minus aqueous plus Ag plus aqueous goes to AgCl solid. Okay, a similar question, and this is really a two-part question, and pretty tricky actually. Okay, what mass of barium sulfate is produced when 100 mils of a 0.1 molar solution of barium chloride is mixed with 100 mils of a 0.1 molar solution of iron 3 sulfate? The mass molecular weight of barium sulfate is given, and first write the molecular total ionic and net ionic equations for this reaction, and then solve. All right, our first step would be to write the molecular equation, but to do that we need to know the chemical formula for each of the constituents in this reaction. We're given barium sulfate's formula up here, but now we need to find barium chloride and iron sulfate. So you can see from, hopefully you can see from the formula of barium sulfate, if you know, remember that SO4 is the sulfate ion has a -2 charge. That means barium must have a +2 charge. The other way you can find that is by looking at barium's place in the periodic table. You know that it's in the second column. It's going to lose 2 electrons to form a noble gas configuration. So what would be the formula for barium chloride? Barium has a 2+ charge. Chlorine, it's a halogen in group 7A. It wants to gain 1 electron, so it's going to be a -1 charge. So we need to make a formula where a molecule in which these charges balance. So we're going to need 2 chlorine atoms for every 1 barium atom. So barium chloride would be BaCl2. Now what about iron 3 sulfate? Now this 3 tells us that it's a +3 charge. And as we've seen before, sulfate is a -2 charge. So how do we combine these so the charge is equal? Well, the easiest way to do that is to drop the charges down in a manner like this. So sulfate has a -2 charge. If we times iron by that, and iron has a +3 charge, so multiply the sulfate ion by 3. So that would give us a formula of Fe2, SO4, 3 SO4s. And you'll see that the charge would be 3 times -2 would be a -6, and 2 times +3 would be a +6. So our charge is equal. So that's the easy way to find the formula of an ionic compound, where you don't know the ratios of the 2 ions in the compound. All right, let's write the molecular equation. So we have barium chloride aqueous plus iron sulfate aqueous
and that goes to barium sulfate, which is our solid precipitate, plus iron chloride. And remember, our iron is +3, so iron chloride, it needs 3 chlorines to balance the charge, and this is also aqueous. Now we have to balance this molecular equation. So a good place to start the balancing process would be on iron. There's two atoms of iron on this side, so we're going to need to add a 2 irons over here. So if we add a 2 on this side, that becomes 2 times 3, or 6 chlorine atoms. And you see that on the left side we only have 2, so we're going to have to multiply that by 3 to balance chlorine. When we do that, we get 3 bariums, and we're going to have to add a coefficient of 3 on the right side to even out the number of bariums. And when we do that, when we look at sulfate, we have 3 sulfates on this side and 3 sulfates on the left side. So now our equation is balanced. So this would be the proper molecular equation, balanced. Now let's look at the total ionic equation. So remember that you're just showing these as their ions. So 3 barium 2 plus, aqueous, plus now we have 3 times 2, that would be 6 Cl minus aqueous, plus 2 Fe3 plus aqueous, plus 3 SO4 minus aqueous. This will go to 3 BaSO4 solid, plus 2 Fe3 plus aqueous, plus 3 times 2, so we have 6 Cl minus aqueous. Now, which are spectator ions? The spectator ions, change the color here. Spectator ions would be the 6 Cl minus, the chlorine, and the 2 iron 3 plus. So we take those out, and we can write our net ionic equation as 3 Ba2 plus aqueous plus 3 SO4 2 minus aqueous goes to 3 BaSO4 solid. Okay, now just to remind ourselves of the solubility rules, we're being told in the question that the barium sulfate formed a precipitate, that was the precipitate, but if we weren't told that, we could look back on our solubility rules and see that the sulfates generally are soluble except when they're combined with lead, mercury, or these 3 group 2A metals, barium being one of those. So that would form a precipitate. Okay, we've written the molecular total and net ionic equations for the reaction. To answer the second part, it would be helpful to have those handy. Okay. So the question's really asking what mass of the precipitate will be produced when you start with a certain concentration of barium chloride and 100 mils of a certain concentration of iron 3 sulfate.
So how do we go about answering this equation? Well, we want to know the mass of barium sulfate, but first we're going to need to find the moles of barium sulfate that are produced. And how do we do that? Well, we're going to need to know first the moles of our starting materials. What were our starting materials? Those were barium chloride and iron sulfate. So if we determine, let's calculate the moles of each of those. And both are the same. We have a 0.1 mole per liter solution, and we have 0.1 liters of that solution. 100 milliliters is 0.1 liters. So in both, we're starting with 0.01 moles of each. And this is where the term limiting reagent comes important. And if you look back on our our total molecular equation, you'd see that the mole ratio we have would be 3 moles of barium chloride reacts with 1 mole of iron sulfate. So which of those would be the limiting reagent? And that is the one that's used most. We have the same number of moles of each. So then we look back at the coefficients in our molecular equation, and we see that for every 1 mole of iron sulfate, we're going to need to use 3 moles of barium chloride. So if we assume that this reaction goes 100% completion, barium chloride would be the limiting reagent. So if we start with 0.01 moles of barium chloride, and we'd have 3 moles of barium sulfate produced for every 3 moles of barium chloride. And again, this molar ratio is from the molecular equation. We're going to produce 0.1 moles of barium sulfate. So that's pretty easy. It's a 1-to-1 molar ratio. We know the moles of barium chloride we started with, so we're going to get the same number of moles of barium sulfate. Now we need to calculate the mass of the barium sulfate. To do that, we take the number of moles times the molecular weight, which is given here. And what we should end up with is about 2.33 grams of barium sulfate precipitate. All right, let's talk about different types of solution. One type of solution you could have is a saturated solution. And this contains the maximum amount of solute that can dissolve in a given volume of solvent at a given temperature. So solubility changes with temperature. So we can talk about the solubility of a substance as the number of grams of it that can dissolve in a particular volume of a solvent. And a saturated solution would be the maximum amount of your solute that will dissolve. You can also have what's known as a supersaturated solution, and this contains more solute than is theoretically possible to be dissolved at a given temperature. Given an example of a saturated solution shown here. and in a saturated solution, shown on the right side, you see that for every sodium and chloride ion that goes into solution, you have a sodium ion and a chloride ion that come back out of solution, so that it's in balance. A supersaturated solution, well, how would you end up with that? One way would you'd heat your solvent, and solubility changes with temperature. So you could heat your solvent up and thus dissolve more of your solute in it, and then as it cools down, and if it's in a very smooth container, it becomes a supersaturated solution. Your solute is still dissolved, but as the temperature goes down, it's over the saturation point, and then all you have to do is add, as shown here with the tweezers, a small rock or something with a nucleation site, and then you get your solid crashing out of solution, as shown here.